Hello everyone and welcome to the OneClass channel. My name is Donna and I'm a recent master's graduate from the Materials Science program from the University of Ontario Institute of Technology, also known as Ontario Tech University. So today we're going to go over some commonly asked questions in chemistry at the high school, college, and university level. So if you needed any help with homework or tutoring, then check out the links in the description below. So now let's just get started on our set of questions for today's session. Okay, so the first question just asks, what is the molar mass of calcium hydroxide? Okay, so to answer this question, we need all of the atomic masses of the atoms that are in calcium hydroxide. And you can just find these values on your periodic table. So the molar mass of calcium hydroxide is equal to the molar mass of calcium plus 2 times the molar mass of oxygen plus 2 times the molar mass of hydrogen. Okay, so the molar mass of calcium is 40.08 grams per mole. And the molar mass of oxygen is around 16 grams per mole. And the molar mass of hydrogen is around 1.01. Okay, so if we were to add all these values up, we get a total molar mass of 74.01 grams per mole. Okay, so let's see what the junior tutor said. To calculate the molar mass of a compound, the molar mass of each element of the compound is multiplied to the number of atoms and summed up. The molar mass of each element can be obtained from the periodic table, and the number of atoms is indicated by the subscripts. Okay, so they showed calcium, oxygen, and hydrogen's atomic masses. Hence, the molar mass of calcium hydroxide is equal to 40.08 plus 32 plus 2.02, which is equal to 74.10. Yeah, so mine should also be 10 or just around 74 grams per mole. Yep, so the solution is correct. Okay, so on to question number 2. Identify the atom with the following ground state electron configuration for its valence shell. So it has an electron configuration of 4s2 3d10. So we know it will be in row 4, and then it's one of the transition metals. So let me just look up a periodic table with all of the different blocks colored in. Okay, so 4s2, you can see here is row 4 containing the potassium and calcium. And then if we count 10 in the transition metals D block section, you'll see that we end up at zinc. So therefore, the element with the ground state electron configuration of 4s2 3d10 is zinc. And the junior tutor said electron configurations can be used to identify an element. The entire electron configuration is not needed, only the electrons in the valence shell. Valence shell electrons are outer shell electrons. An electron ending in the d orbital valence shell is usually found in the transition elements group. The element is zinc. So this solution is correct. Okay, so question 3. How does a Lewis acid differ from a bronsted acid? Okay, so let me write down the two definitions. So a Lewis acid is an electron pair acceptor and I'll also just write down the definition of a Lewis base, which, as you can guess, is an electron pair donor. Okay, so as an example, if we had a fluorine ion plus boron trifluoride makes BF4 minus. In this case, the Lewis base is the negatively charged fluorine ion, and the Lewis acid is the BF3. And together, they form an acid-base product. Okay, so that's the example for a Lewis acid and a Lewis base. Now let's compare it to a Bronsted acid and Bronsted base. There's like an accent in the O. So a Bronsted acid is defined as a proton donor. So protons are just positively charged hydrogens. And similarly, a Bronsted base is a proton acceptor. Okay, so you can already kind of see how it would differ from a Lewis acid, since both the Lewis acid and the Lewis base they didn't contain hydrogen. But in the case of the Bronsted acid and the Bronsted base, as an example, let's say we had NH3 plus hydrochloric acid makes NH4 plus Cl minus. Okay, so we can see that the base is our NH3. So I'll just say bronsted base. And our bronsted acid is HCl. And we know this because the NH3 was the one that accepted the proton to become NH4+, and the HCl was the one that donated the proton, and it became Cl-. So now NH4+ becomes our conjugate acid, and Cl- is our conjugate base. And we know this because in the reverse reaction, if we were to go the opposite direction, NH4+ would be the one to donate the proton, and the Cl- would be the one to accept the proton. Okay, so now let's see what the junior tutor said. Lewis acids and bases are identified in terms of their ability to accept or donate electron pairs, while Bronsted acids and bases are identified in terms of their ability to donate or accept protons. Lewis acids are electron pair acceptors, while Bronsted acids are proton donors. Yep, so this solution is correct. Okay, so question 4. What is the noble gas electron configuration for silicon? Okay, so first let's just find the electron configuration for silicon. So it is found here on the periodic table, atomic number 14. So you'll notice with this periodic table, all the different blocks are highlighted in different colors. So for example, the S block is in light blue, the P block is in green, the D block, which is our transition metals, is orange, and the F block is that dark pink, which is the lanthanides and actinides. Okay, so to find electron configuration, we're going to be starting from hydrogen and moving left to right and down across the periodic table. And then you just write the row number, and then following that is its block number, and then showing all the electrons in that orbital. So in the case of silicon, which is here, we'll start off at hydrogen and just write 1s2, and then moving down to the next row is 2s2, and then moving across is 2p6, and then down to the next row is 3s2, and then lastly for silicon we count 1, 2, so then it's just 3p2. Okay, so now that we have the long version of silicon's electron configuration, the question asks for its noble gas electron configuration. So this is also known as like the shorthand electron configuration, and it's pretty easy. All you have to do is look at the noble gas that comes before silicon. So in this case, it's neon, and you just put it in square brackets. And then from there, you just go to the next row and carry out how you would normally find electron configuration. So it would be neon, 3s2, 3p2. Okay, so let's see what the junior tutor said. Electrons fill orbitals in pairs from closest to the nucleus outward according to energy level. Silicon's atomic number is 14, and the resulting ground state electron configuration for silicon is 1s2, 2s2, 2p6, 3s2, 3p2. Silicon is not a noble gas, but its configuration can be shown by the use of a noble gas. You build a simplified version to write a configuration using the noble gas. To do this, you must refer back to the noble gas before the element on which you are operating. The noble gas, which contains 10 electrons, immediately before the silicon is neon with an atomic number of 10. The resulting configuration of silicon is then turned to neon 3s2, 3p2. Yep, so the solution is correct. Okay, so on to question 5. What is the product of the reaction below? Draw all hydrogen atoms. Okay, so let's draw out the reactant. So we have a 4-carbon chain with a double bond at the end, and it is added with chlorine. Okay, so I'm going to draw out a mechanism that may occur. So this double bond will come and attack one of the chlorines, kicking off the second one. And we have an intermediate. That now has a single bond and a newly attached chlorine atom where the double bond used to be. And then this leaves us with this positively charged carbon. But then one of the chlorines that was formed in the previous step that now has a negative charge will come and neutralize that positively charged carbon, which gives us our final product. So now there are 2 chlorines where the double bond used to be. And if we were to name this, I like to first find out my parent chain, which is the longest carbon chain that contains all of the most important substituents. And then from there, you would number the carbons, and we want the least number possible. So I'm going to start numbering where our chlorines are. Okay, so again, we have that 4-carbon chain. And then to show which carbons the chlorines are on, it would just be carbon 1, carbon 2. And then to show that there are 2 chlorines, we would use the prefix di. And then chloro. And then our parent chain is 4 carbons, so it is butane. Okay, so let's see what the junior tutor said. The given reaction above is an addition reaction of an alkene. In our example, the alkene is 1-butene, and the electrophile to be added is Cl2. Since Cl2 has 2 chlorine atoms which are alike, we do not need to think about Markovnikov's rule. The reaction mechanism will be as follows. Okay, so they have the same kind of mechanism. First, an instantaneous polarity will be affected on the Cl2 molecule, where one chlorine would be the partial positive center and the other the partial negative center. Then the pi bond of propylene will attack the partial positive chlorine, and then the chlorine-chlorine bond would break, which would result to a carbocation of 1-butene and a chlorine anion. Yep, so that's what they got here. And then the chlorine anion is and the formed carbocation. So carbocation, or it's just another word to say a positively charged carbon ion. So this will react to form the new molecule, a dichloral alkane. In our example, the alkane formed is 1,2-dichlorobutane, and the structure is shown below. Yep, so the solution is correct. Okay, so on to question 6, which just asks, how would you balance this equation? So we have CH4 plus O2, leave a space. Okay, so when balancing questions that contain kind of like the same atom and multiple compounds, so for example, there's an oxygen on our reactants, and then there's also an oxygen in carbon dioxide and also in water. So I know I want to balance my oxygen atoms last because I don't have to like double take and go back and try to balance oxygen after the fact. So first, I would usually just balance the carbons and then the hydrogens and then the oxygens. But in the case of carbon, there is only one carbon on our reactant side and one carbon on our product side, so it's already balanced. So the first step is just to balance my hydrogens. So on our reactant side, there are 4 hydrogens, and on our product side, there are 2. So I'm just going to put a coefficient of 2 in front of HCO just to show that we need 4 hydrogens on the product side as well. Okay, so now that all the hydrogens are balanced, now I want to balance my oxygens. So on our product side, you'll see we have 2 plus 2, so there are 4 oxygens in our product side. So I'm going to write coefficient of 2 in front of the O2 in our reactant side. And now everything should be balanced. So we can double check. There is 1 carbon, there's 4 hydrogens, and then also 4 oxygens. Okay, so let's see what the junior tutor said. To balance this equation, we perform balancing by inspection, which is basically trial and error. There are some techniques to guide us in balancing the equation, but first we balance the element that is not an oxygen or hydrogen by multiplying it with a coefficient so that the number of molecules of the atoms in the reactant side of the equation is equal to that on the product side. We do not need to balance carbon since both the number of carbons are equal to each other. So we balanced hydrogen next, and to balance hydrogen, we multiply H2O by 2. Lastly, we balance oxygen by multiplying O2 by 2. We check the equation if it is balanced by accounting for the number of moles of elements in each, and this is shown in Table 1. Yep. So the solution is correct. Okay, so question 7 just asks, what does PhD stand for? So PhD stands for Doctor of Philosophy. Okay, so basically it is an academic degree. And in most countries, you need a PhD to get qualified to teach their subject at a university level. Or you can work in the industry in a specialized position in that field. Okay, so the junior tutor said that a PhD or a Doctor of Philosophy is a doctoral research degree or program that is normally the highest level of academic qualification you can achieve in most countries. Yep, so this solution is correct. Okay, so question 8. What is a hydrocarbon? Okay, so even just looking at the name hydrocarbon, we can kind of guess as to what it is. It's an organic compound that consists of both hydrogen and carbons. Okay, so for obvious reasons, hydro and then carbon. Okay, so I'll have some examples. So example, you can have a carbon that has 4 hydrogens attached to it. And this is just methane. Or you could have a carbon ring So this is an aromatic 6-membered ring that only contains carbons and hydrogens, and it is called benzene. This is another example. Okay, so hydrocarbons, they are good for us humans because they provide energy when they undergo combustion with oxygen. Okay, so let's have an example of a combustion reaction. So typically, you have your hydrocarbon. So for example, let's say hexane. And combustion reactions will always have oxygen as a reactant, and the products will be CO2 plus water. Okay, so now to balance this reaction, I'll balance my carbons first. So there are 6 carbons on our reactant side. I'll put 6 in front of CO2 to balance out the carbons. And then next, I'll balance out my hydrogens. So there are 14 hydrogens in our reactant side, so I'm going to put a coefficient of 7 in front of H2O. And lastly, we can balance out our oxygen. Okay, so if we count it out, in the reactant side, it is 12 plus 7, which is 19. So in front of O2, I'm going to put 19 over 2. But in order to get everything as a whole number, to get rid of that fraction, I'll multiply this whole reaction by 2. So this gives us 2 hexane plus 19 O2 makes 12 CO2 plus 14 H2O. Okay, so if we quickly double check, we should have 12 carbons, 28 hydrogens, and then however many oxygens that is. 19 times 2, so 38. Okay, so the junior tutor said, hydrocarbons are organic compounds that consist of carbon and hydrogen atoms. These are naturally occurring compounds that make up the most common energy resources such as crude oil, natural gas, coal, and others. They provide energy because they are highly combustible, producing carbon dioxide and water, as well as heat when burned through the use of oxygen. There are 4 types of hydrocarbons. Alkanes are single-bonded carbon and hydrogen with the general formula CnH2n plus 2. So however many carbons you have, so let's say you had 2 carbons, to find out how many hydrogens you would have in that alkane, it would be 2 times 2, which is 4 plus 2, so 6. And then alkenes are double bonded carbon and hydrogen with the general formula CnH2n. Alkynes are triple bonded carbon and hydrogen with the general formula CnH2n minus 2. And then aromatic compounds like our benzene contain 1 or more rings with pi electrons delocalized all the way around them with the general formula CnHn. Yep, so this solution is correct. Okay, so question 9. Consider this system at equilibrium. So we have A plus B. Oh wait, A is in equilibrium with B. And its delta H value is equal to negative 650 kilojoules per mole. And then the question asks, what can be said about Q and K immediately after an increase in temperature? Okay, so first let's kind of analyze our reaction. So delta H is enthalpy. So enthalpy is negative. So this tells us that the reaction is exothermic. So when we have an exothermic reaction, that means heat is produced, or heat is a product. Okay, so I'll also define what Q and A kind of represent. So K is the concentration of B over the concentration of A at equilibrium. And Q similarly is also the concentration of B over the concentration of A, but this is at reaction conditions. So when we, let's try a different color. Okay, so when temperature is increased, we can also look at this as that we are adding heat. So that's the same thing as saying that we are adding more product, since heat is a product of this reaction. So therefore, the reaction will shift to the left. So to our reactant side, so when reaction shifts to the left, then the value of K decreases. Okay, so A is favored. And the value of Q will be greater than K. Because at reaction conditions, yeah. Okay, so let's see what the junior tutor said. Because the enthalpy change is negative, the reaction gives off heat and it's exothermic. The expressions for the equilibrium constant and the reaction quotient Q are as follows. B over A, either at equilibrium or at reaction conditions. In an exothermic reaction, heat is a product, therefore increasing the temperature of this system will shift the reaction to the left in order to minimize the change in temperature. Thus, reactant A will be favored and K will decrease. Yep, so the solution is correct. So every time there's a change in the reaction conditions, the reaction wants to go towards something that will make it more in equilibrium. So that's why when more product is added, then it kind of shifts more to the reactants to kind of balance it out. Okay, so question 10. Given the balanced equation, so I'll write it down as well, we have calcium carbonate plus 2 hydrochloric acid makes calcium chloride plus H2O plus CO2. Select all statements that correctly describe how to calculate the mass of calcium carbonate that will react with 72.5 milliliters of a 0.25 mole per liter solution of HCl. The molar mass of calcium carbonate is 109 grams per mole. Okay, so first I'll just try to answer the question first before looking at all of the different variables they give us and answers. So let's just write down everything that we know and what we're looking for. So we're looking for the mass of calcium carbonate in grams. And they also give us the molar mass of calcium carbonate, which is 100.09 grams per mole. In the case of hydrochloric acid, they give us the volume, which is 72.5 milliliters. But I'll convert it to liters so that everything is in the same units. And they gave us the concentration of this solution as well, which is 0.25, and then capital M is the same as moles per liter. Okay, so that's everything we know so far. So the first step is to find the number of moles of HCl. And to do that, we know that to find number of moles, you just need to calculate concentration by volume. So the concentration was 0.25 moles per liter, and the volume is 0.0725 liters. And then if we multiply it out, we get 0.0181 moles of HCl. And this is how many moles were consumed Okay, so now step 2 is to now find the number of moles of calcium carbonate. Okay, so to do that, we would use mole ratios. That's why it's important to balance your reactions first. Okay, so that we know that for every 2 moles of HCl that react, 1 mole of calcium carbonate reacts. So we do the mole ratio, 1 mole calcium carbonate for every 2 moles of HCl. So you'll see the moles of HCl cancel out. We divide that by 2. And we get 9.05 times 10 to the negative 3 moles of CaCO3 that reacts. Okay, so now that we have the number of moles of calcium carbonate, we can find the mass. So the mass is just the number of moles times the molar mass. So the number of moles is what we found in the previous step, 9.05 times 10 to the negative 3 moles. And the molar mass was given in the question. It is 100.09 grams per mole. And this gives us an answer of 0.906 grams. Okay, so now let's look at the options they give us in the questions. 3.62 times 10 to the 2 moles of CaCO3 will react, so that's not correct. 0.906 grams of CaCO3 will react, so that is correct. I'm just going to do therefore B. So let's look at the other options. 0.29 moles of HCl are used. Nope. And then the conversion factor is 0.25 mole HCl per 1 liter will be used as written in the calculation. So by conversion factor, I think they might mean the mole ratio step. So the last one isn't correct as well. Okay, so the junior tutor said, first calculate number of moles using molarity times volume. And they ended up getting 0.0181. And then they did the mole ratio step. So they divided it by 2, 0.00905. And then they found the mass of calcium carbonate, which was 0.906. Okay, so this solution is correct. I'm just going to put the conversion factor for the number of moles is 1 mole Okay, so on to question number 11. What is the Lewis structure of NH3? Okay, so when I find the Lewis structures of a certain compound, I first like to find out the total number of valence electrons. So in the case of NH3, for nitrogen, there are 5 valence electrons, and for hydrogen, each hydrogen atom has 1 valence electron, and there's 3 of them. So the total number would be 8. Okay, so to write out the Lewis structures, you first need to try and figure out which atom is your central atom and which atoms are your terminal atoms. So in the case of NH3, since there are 3 hydrogens, it is safe to assume that nitrogen is our central atom, and then all the hydrogen atoms are spread out around it. Okay, so after you show your basic skeleton of the Lewis structure, let's see how many electrons I have drawn so far. So every bond contains 2 electrons, and there are 3 bonds. So I have drawn 6, but I need a total of 8. So for the last 2 electrons, I'll add them as lone pairs on my nitrogen. So this is because since hydrogen only has 1 electron, it won't have any like lone pairs anywhere on it. Hydrogens will only form a single bond. So the same thing goes for like chlorine and fluorine. It's not likely you'll see them having a bond and like multiple other bonds around it. Okay, so we have 8 electrons. Nitrogen has a total valence shell. So this is the Lewis structure of NH3. Okay, so the junior tutor said, the Lewis structure of ammonia is 3 hydrogen atoms bonded to a nitrogen atom, which is the center, with a lone pair of electrons on top. The Lewis dot structure represents the arrangements of electrons, shown as dots, between atoms in a molecule. The atoms must follow the octet rule or the tendency of atoms to prefer to have 8 electrons in the valence shell. The individual formal charge of each atom, as well as the overall formal charge of the molecule, must be satisfied. In drawing the electron dot structure of ammonia, step 1, draw the skeletal structure of NH3 with nitrogen at the center. Step 2, calculate the total number of valence electrons in the molecule. So I like to do this one first, but I guess it doesn't matter too much. But they found it to be 5 plus 3, which is equal to 8. Step 3, to distribute the electrons as dots. So note that octet rule must be satisfied for nitrogen atom. However, hydrogen can only share 2 electrons. Step 4, replace the 2 electrons with a single bond between nitrogen and hydrogen. A lone pair of electrons will be left at the top of the central nitrogen atom. Yep, so this solution is correct. Okay, so question 12 just asks, what is an alkyl group? Alkyl group. So these groups are formed when an alkane has 1 hydrogen removed. So the general formula for an alkyl group, CN H2N plus 1. So you can find alkyl groups as like substituents. And I'll just show a quick example. So let's say you had CH4, which is methane. If it were to lose one of its hydrogens, it becomes the group methyl. I'll just have another example because we have time. Let's say we had a long carbon chain. And we had groups sticking out like this. There. So to name this, you would circle the longest chain of carbons, and then if we were to number them, let's start from this end. So you want to try to have the lowest number of carbons in your name. Okay. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So in this case, we have on carbon 4 and 5 2 methyl groups, and then carbon 7 is a 2 carbon side chain. So this is ethyl. Then this is the methyl group, and this is another methyl group. Okay, so these are the examples of different alkyl groups you could have. Okay, so we might as well name this as well. So on carbon 7, we have an ethyl group, 7 ethyl, carbons 4 and 5. We have 2 methyl groups, so dimethyl. And then if we wanted to find the name of the parent, let's look it up. So I'll just search naming organic compounds part. When you have a 10 carbon chain, it has the root word of dec. And since there are no double bonds or triple bonds, it will just be decane. Okay, so this is 7 ethyl 4, 5 dimethyl decane. And the junior tutor just said alkyl is a functional group of organic hydrocarbons with the general formula CnH2n+1. It is a substituent formed from alkane with one hydrogen atom removed. Thus, in naming alkyl groups, the suffix ane is replaced by -il. For example, methane to methyl. Yep, so this solution is correct. Okay, so I think that is all the time we have for this Q&A. And if you enjoyed today's Q&A and you'd like to be notified of when we do this next, please hit the subscribe button and notification bell below. And if you'd like to submit a question of your own, then check out the links in the description. And also, if you like today's video, you can leave it a like and a comment. And don't forget to share it with your friends and classmates if they needed any help with chemistry. This has been Donna from OneClass, and I hope to see you soon. Bye.